Hi, my name is Ivona. I have an ongoing thing with Amir. He always hoards the time. He always gets, like ocean products. He has one thing that he has to talk about, which is remote sensor reflectance, and I have 25 million products. But of course, it is much more important because he has to, that's where everything starts, no? But he now owes me 1 bottle of cognac and 4 bottles of wine. So my name is Ivona. You haven't seen me yesterday. Some of you know me from some other classes. I kind of hoard and take care of the PACE biogeochemistry, but I'm going to be talking about all ocean products here. I kind of try to give you like a minimal amount of things that you have to know in order to use them, and I'll try to kind of like jump and connect on these things that. Am I in a good spot? Good. Okay. I just like giving like the chair. Kind of try to connect to some of the things that Amir has said. If you, remember the story about absorbing gases and issues in atmospheric correction, and explain you, like, when you're going forward, if you think about making your own algorithms to detect whatever you want to detect and use the information, I want you to think about how do we got to that point, what are the assumptions, and I can't cover all 25 million products that we have. I'll cover some of them. But we have information about these things on our website. And please go, I know like when you hear ATBD or the technical documents, it's like, bleh. But really do go read them because they're assumptions. Like the way we make algorithms, it's not always empiric. We make assumptions. We do. That's models, no? So understand those assumptions and don't come back to me because all of us are going to probably review your papers, and if you tell me, it's like, oh, I found this fantastic connection between KD and chlorophyll, of course you did, and of course this paper is not going to get published. So just kind of like think about what goes into the algorithms. What are the assumptions that are made as you're going forward and publish those amazing Nature papers using PACE data? I'm going to go really fast to certain things because we don't have time. Well, we know that we love the oceans. Oceans are great. They have dolphins and everything else. There's food in them. It controls our climate, and most of that life that we love in the ocean, and quite a lot of that control of the climate, it's going back to the existence of the phytoplankton, and those are the things that I care about. And they are teeny tiny creatures that live in the ocean. They're plant-like, but they're really not plants, but similar to plants, they can do photosynthesis. And I apologize to all the hardcore biologists here, but we have aerosol people, so I'm just going to go through some basics, okay? So photosynthesis is a process through which we kind of I wish, plants or phytoplankton, anybody who has chlorophyll can capture this carbon dioxide with a little bit of help of the light and a little bit of water. We can produce the sugars that feed all those beautiful dolphins ultimately. And, as a side note, it gives us some oxygen. And that's a very important process, and that's why we follow these plants because they're beginning of the life in the ocean, and they control the climate and so on. The cool stuff about PACE is that PACE takes a step forward, not offering us only just the existence of phytoplankton and how much of that stuff there is, but it gives us some diversity to start thinking about specific ecosystem or specific processes in the ocean. And the coolest thing about PACE is that we can hook up all that stuff to the atmospheric processes and start talking about, deposition of the aerosol into the ocean, how the ocean is reacting, or how is ocean provoking clouds to become clouds, or maybe not, because I heard that's a very crazy idea there among the cloud people. So photosynthesis 101, I can talk about this for 3 years. So you're going to get 30 seconds. This is the process. Photosynthesis is happy algae. Chlorophyll is the most important pigment, but it's not the only one, no. And that's the pigment that allows the capture of the light and conversion of the inorganic carbon into the organic carbon. And this is like covering one of the carbons in the molecule of sugar to the right. I don't know what's happening with my slides, but there's like on the right-hand side of that diatom, there's sugars. It's not just like 12O6. There's hydrogen mixing and carbon mixing, but you get sugars on that side. And that sugar feeds, once again, marine ecosystem and propels the pumping of the carbon through the biological carbon pump that I'm not going to go into it. This phytoplankton is not only green. Now, it comes in many different colors, shapes, and sizes. And their size and sometimes shape and even sometimes color defines the role that they play in the marine ecosystem. Defines also the role that they play in the oceanic carbon cycle. Will they be consumed and pooped out by the big zooplankton? Will they just like float and forever in the surface of the ocean, really not contribute to that drawdown of the carbon? Very much so, that's determined by what they are, no? But luckily for us, these are all the properties that also determine their ocean color. So those two things are very relatable. That's why we can use ocean color to talk about phytoplankton and its diversity. However, over the last 25 years, we've been seeing only green. and this is where PACE takes a step forward and takes us from this realm of green, of measuring only phytoplankton, chlorophyll, to everything else. And because green cannot observe the diversity that is in there. So I'm going to be talking about not only phytoplankton, but mostly phytoplankton because they didn't tell me what to talk about, so I'm going to talk about what I like, okay? PACE, Amir got you to the surface of the ocean. I'm going to take you below surface of the ocean, and it's going to start doing by itself. I should not click, and now it's not going to do it, so let's go back. Okay, I go here, and I don't touch. Is that what happens? I should not touch and things should move, but they're not moving. All right, we're going to forget about this slide. We're going to go here. So the way I think about ocean data products is best to think about them in L2 suites. And this is like, I think nothing has changed in version 2, but we have these suites in L2, and some of these products are, of course, available in L3, and some of them, as you're going to see, we're going to start calling level 4 products, and I'm going to explain you why. But I'm going to take you through these suites and pick some of them that are my favorite ones and the ones that I think might be interesting for this crowd and the ones that I like, and kind of take you down the line of the ocean, PACE ocean products. So one other stuff that is exciting about the PACE products, PACE level 2 suites, is for the first time we actually have uncertainties. And I don't know how much of you guys are happy about uncertainties, but at one point, some of you at least are going to have to write a NASA proposal, and there's that portion where you have to explain your uncertainties. And now you can talk about them, and we're going to give it to you. Thanks to all that stuff that Amir was talking about, and I don't know how many of you was actually paying attention and lost it on the first formula, but we're capable of producing remote sensing reflectance uncertainties. And we have also built a pipeline to take these uncertainties and also take some algorithmic uncertainties into these final products that you care about. So if you open up your chlorophyll L2 file, BGC L2 file, you're going to have also chlorophyll uncertainties. Why do you care? Maybe you don't care, or maybe you care. Maybe you are into water quality stuff, and you have to use these uncertainties to kind of say some significance of the change of that chlorophyll. Is it getting naughty or is it not getting naughty? Maybe you're your system modeler and you've been just assuming 10% for the, since the beginning of the lifetime. Now we're giving you these uncertainties. And you can take them down the pipeline. This is just an example on the right-hand side of how the uncertainties accumulate in different estimates of the carbon fluxes in the ocean. They accumulate as you go from assumptions to assumptions. And we're kind of providing these values now for you that you can take them and put them in your models and so on. So I'm excited about them. Okay, let's go to the first suite. Apparent visible wavelength falls in the first suite. It's really not truly an apparent optical properties, but let's call it. And I saw it mentioned somewhere around the way, and it's a really cool thing. So it's a very, very elegant and cheap solution for, especially for biologists like me, who are really not, I cannot think in 250 wavelengths. And this gives you one number. No, it's pretty much a color of the ocean. And if you think about it, a cheap way to do some optical characterizations of the water where you don't have to do fuzzy logic, machine learning, or something, use this. I used it before in one paper, like this plot up there, to kind of just say, look, these are, I think, significantly different ecosystems shown in the colors, which are pretty much different colors of AVW. AVW is also useful to check how good the quality of your data is. No? We do our best to give you the best remote sensing reflectance possible, but there's lots of data passing through, and we can't quality control everything. So Ryan Vandermeulen, because he's insane and awesome, he together with Heidi Dearson, who's the same way, has developed this thing called QUIP. And I don't think that we're producing it, but you can use L2Gen to use it, where they have defined this relationship between AVW and NDI for where if these reflectances, if these pixels fall in this relationship, it's a good QUIP. You can use these reflectances. But if they fall outside, there's an issue with your reflectance, no? So if it falls, in this case, above, I think there was a case of a shallow water. If it falls below, there's a glint or something like that. But as you're going forward and develop your algorithms and stuff, you can use AVW to structure your water masses and also maybe check the quality of your remote sensor reflectance. That's there for you. It's an L2Gen. I'm going to go boom, boom, boom through these, okay? Just normalized fluorescent line height. Not a sexy product. I love it. So going back to that photosynthesis that I mentioned, when algae or anything takes that light, those electrons, those photons kind of flow through the bunch of different systems that I don't have time to think about and talk about or present to you or explain to you. But some of that energy goes in photosynthesis, awesome. Quite a lot of that energy goes into heat. But there's some extra energy that hasn't been used up, and that pops up on the other side of the spectra as a fluorescence. No, it just pops up. So these are the photons with a little bit less energy, and they jump up there. And this is what we can see from space. And in a sense, it's a measurement of the happiness of a cell. If the phytoplankton is stressed because it didn't have good yum-yums like iron, it's going to fluoresce different than the same cell that had lots of good nutrients. No? Sometimes it can be also different types of phytoplankton will fluoresce in different ways. There's so many good usages for that, and there's quite a lot of work that has been done by Toby Westbury and Mike Barenfeld on using this fluorescent line height. I like it. And with PACE, we can derive it in a little bit better way just because we have a higher spectral region. So in this plot, you can see the differences in how we derived it from MODIS and how we are currently deriving it from PACE. You can see also that it's crossed over in our thing because we're not producing it for you. Why? Let's go back to everything that Amir has said. And if you remember, there's some naughty regions in OCI spectra that we still have a teeny tiny bit of issues with absorbing aerosols. And of course, right around 685, where we have this fluorescent peak, we still have a little bit of an issue with these absorbing aerosols. So that's why we kicked it out of the version 1 of the data. And whenever the people that Brian is associated with produce me new files, I'm going to check out this fluorescent line height and see if we can start producing it. I'm sorry?
Not aerosols, gases.
Sorry, gases, same thing. The thing's up in the sky. I apologize. It's not a marine stratocumulus. That's the only one that I can recognize. Thank you, sorry. But look up for it because it can be cool for you. It can be just kind of tell you cool little things. Combine it with other things that you're using. Just keep an eye on it, no? Don't overextend the power of it, but keep an eye on it, no? Okay, the next suite is inherent optical properties. So these are the properties that have to do with something that is in the ocean and how they react with the things, the light that is shining on them, no? And in theory, when the light hits something, anything, water, molecule, phytoplankton, dirt, that light can be either absorbed or scattered. And what we see as ocean color is very much relatable to that ratio of scattering and absorption. And that's why we can very easily derive, we can derive inherent optical properties from the ocean color, from the ocean color itself. On the other side, these optical properties are relatable to the type of phytoplankton, as I said before, to their size, to their morphology, to their color. So all these things are really well together. How do we derive IOPs? There are many different ways. There's like machine learning ways, there's empirical approaches, there's modeling approaches. Currently on the launch, we're using something that's called GIOP, Generalized Inherent Optical Properties Algorithm. The author is over there, the gray dude. So just bug him about the details. But one thing that what you want to know is that this GIOP algorithm is very modular. There's a default thing that you're going to get when you take your L2 or your L3. But you can also go and tinker with it and change certain assumptions. And these assumptions are really important to understand. Like, for example, we make an assumption about basic spectra of the phytoplankton. And so if you want to use this to derive different types of phytoplankton absorption spectra, maybe it's not the best way to go because we make assumptions. If this is something you're going to use, go and check out the paper, look at the ATBD, and start tinkering and start maybe changing the outputs. There's so many different things that you can tinker with. And as you're going to see, several of the phytoplankton community structure algorithms that we're going to be pushing out are actually playing with GIOP to derive phytoplankton community structure. Here, in homage to Lachlan McKenna, who's the person who takes care of our inherent optical properties, it took just like a base image, offshore Australia, and just plotted for you 3 different absorptions of the phytoplankton. And here you can see your typical behavior of the chlorophyll, and you can see that as we're going from the open ocean, the blue, to the orange, whereas the coastal ocean, there's an increase in absorption, but the shape doesn't change a lot. And we know, I know for a fact, everybody knows for a fact that the community composition changes. So it's not going to change because there's certain assumptions that it's small. It can't do everything. It can't make a coffee for you, solve the problems of the hunger in the world, and give you phytoplankton structure. It cannot. It can give you only so much. So you have to understand what it can give you in order for you to take it further down the line. Yeah, and this is just a comparison. So on the bottom is what I get from GIOP, which is great. We can't expect more. On the top is an example of absorption spectra of a bunch of different cultures in the lab. So there's a big difference, no? Just so you know, for the people who have never seen and measured absorption in the lab, it's very diverse. Because we have lots of different pigments, no? Okay, biogeochemistry suite, that's the one that I love and take care of. It's your chlorophyll A, is our bread and butter. Everybody loves chlorophyll A. The algorithm that we use in PACE is very similar to the ones that we always used before the last 20 years. We occasionally change the coefficients as we get more data, but it's for the last, I don't know, 5 or 6 years or longer. It has been probably longer. It has been a mixture of two different algorithms. One that is taking advantage of the fact that there's a polynomial relationship between that's blue and green and red and chlorophyll concentration. And then the second part is the fact that in a really, really low chlorophyll ocean, majority of the stuff they are giving ocean color are actually associated with the phytoplankton. So they do this line height in the center, like the green, just measure like what's the line height of the green. A mixture of this product gives you a global chlorophyll algorithm. No, we currently on launch have been using CWIS coefficients. That works great for now until we get the data and we can retrain this stuff. And really soon on in March, we right away had this beautiful global image of the chlorophyll that I'm very, very in love with, and it's beautiful. This is a global chlorophyll. You know, there's many different approaches through which you can do chlorophyll. If you're working in specific embayment or so on, the chlorophyll might not work for you. I'm completely aware. We have a couple of things in the pipeline. They're associated with the phytoplankton community structure. They're going to give you different estimates of total chlorophyll as well. We have some machine learning regional chlorophylls. And I'm going to show you through this PCC a way that maybe you can retrain certain things and develop your own chlorophyll. But again, this is a global algorithm. This is the one that best works around you everywhere in the world. If you go in Gulf of Maine, it might not work that great. But this is where you guys learning cool things so you can develop a better one for that area. Carbon stocks, this is what I like to talk about. Carbon is important. You know, like if you think about the money in the ocean, it's not chlorophyll, it's carbon. You know, that's how everything flows. That's how the energy flows, with that carbon. And understanding how ocean affects the climate, it's really important for us to understand the size of the stocks and exchange of the carbon through these stocks. So we can talk about dissolved organic carbon that nobody likes except a small number of people in the world, like Antonio Menino, who's part of our lab. But that's a really important part. That's your like dissolved poo and pee and other things and sugars and things that ocean things produce. There's lots of carbon in the ocean. We don't have an algorithm for that yet. We're trying to implement some testing algorithm. The one that we care a lot about is the particular organic carbon because it's directly relatable to that photosynthesis, no? And we have an algorithm for that. Small portion of that, like a 30% overall, is the phytoplankton carbon. That's the one that is associated with the phytoplankton itself. So the rest of it is detritus, poop, zooplankton, teeny tiny zooplankton, and so on. And then there's PIC that is really, really teeny tiny, and that's particulate inorganic carbon. That's your calcium carbonate that is in the shells of some of the phytoplankton or some of the zooplankton, some that just resuspended by the corals and things like that. We don't care about it too much, but it's really important because it has this really tricky role when it comes to the carbon cycle in the ocean. And it's something that we want to keep an eye on because it's a good estimate of the response of oceanic ecosystems to climate change and some other, like, you know, acidification processes and so on. We don't have currently a PIC algorithm because the current PIC algorithms are really not performing well. So we're going to go forward and take a deep breather and see what we can do with that one. I didn't get that one. Our carbon products are very simple. On the left-hand side, it's the newest POC that is applied for all our emissions, I think, but it's definitely applied for PACE. It's similar to chlorophyll, a mixture of polynomial and line height. Very elegant, very nice, works great. On the right-hand side is something that Jason Graf published a long time ago. I never really thought there's going to be an algorithm, but it is now. So we use GIOP output to get backscattering. Backscattering times his paper gives us phytoplankton carbon. And then you can put that and take it from the PACE, and you can look at the beginning of the spring. Now, this is the middle of the spring bloom in North Atlantic. And it looks very similar. On the left-hand side is your particular organic carbon. That is everything. And then phytoplankton carbon is a portion of it. But if you stare long enough into it and actually make it, you know, or make like one minus the other one, you're going to start seeing patterns, different patterns, which is kind of cool. no, and showing you areas where there's more phytoplankton carbon versus other stuff and so on. And what really makes me happy that that ratio between these two is around 30%, so we're good, no? So that's there for you. Advanced products, something that everybody's really happy about and looking forward to and wants to party with. And these are the ones that we have not released yet. We're in the process of releasing them, but as I know you guys are going to be playing with at least one of them, which is Moana. If you have questions about Moana, the author is there, bug her, and ask her how Moana got the name too. That was a very deep discussion. But we're going to have currently, I think, 4 different paste community composition algorithms in suite. Some of them are going to give you pigment composition. Some of them are going to give you carbon concentration. Some of them are going to give you actual cell abundance. No? And that one is limited for the Atlantic only. We're also going to have a primary productivity algorithm. As of Friday, has been finally accepted, the version by the authors, so we can go forward now. And that's going to be a level 4 algorithm, and I'll explain a little bit about it. And we're going to have a bunch of regional little things for you to play with. Either they're going to be in level 2 only, so I mean like in code, or just maybe some of them are going to produce. I'm not sure about that part. But Moana is the algorithm that we use for our first image, and probably everybody has seen this beauty. And I think Karina is going to show you how to make these cool images. I was trying to make something, and just like, it looks like poop. I just cannot do this. My plots don't look that cool. And Moana is really, it's a very elegant way. So it's using empirical data. It's only for Atlantic. It's using remote sensor reflectance in 420 to 660 region, which is kind of cool because it'll take you back to this schematic, and it's kind of avoiding all the boo-boo regions in ARS. That's good. And then it's using also sea surface temperature, combining that through PCA and multivariate regression with in situ data to get the composition of 3 specific phytoplankton types for Atlantic. These are the teeny tiny things that I really don't like to think about. They're extremely important, and they make the center, like the oceanic gyre stick. Karina's going to lead you through how to play with Moana and how to get that. As I said, Moana is done only for Atlantic, but if you're sitting on some kind of big data set of the picoeukaryotes, Synechococcus, and things like that, the code can be retrained to be used in other oceans. We just didn't have enough data set to retrain it for anything else. Pigment-based PCCs are something called GPIG, which is a Gaussian pigment, and SDP, which stands for spectroderivative pigments or Sasha Dillon pigments. And SDP was published by Sasha and Dillon. And it's a model that it's taking remote sensor reflectance, deriving IOPs, and now jumping on that assumption that we're really bad in getting good absorption from GIOP on any model of GIOP, and taking that IOP, remodeling, recalculating remote sensor reflectance, and take that, now calculating remote sensor reflectance and minusing that from the original one. So what you get is this difference. And it's a difference because the assumptions that we make in a model, no? So she knows that there are assumptions that we made in a model based on absorption spectra, so she's looking at the difference. And the difference is going to be associated with all the remaining pigments, all the crazy stuff that we want to get to. So that's how they're playing around. So ultimately, they do some derivatives, they do PCA, and they get you 13 different pigments. One cool stuff about implementation that we're trying to get is that in order to get you from derivative to the pigments, is we just take derivatives times a table that was done by empirical data. We're going to try to output also these derivatives so you can train it in your own region and see if you can make a specific one for, I don't know, coastal Brazil or like Gulf of Alaska or something like that. So that's going to be adaptable for you as well. This is an L2 testing, and it's awaiting validation data. Similar way, GPIG is going to give you 4 different pigments. It's doing also deriving IOPs, looking at Gaussian peaks that are going to be dominant because of the behavior of different pigments in that absorption spectra, and then times something gives you pigments. We're going to also export these Gaussian pigments so you can maybe train it in your region to get a local product. And this is, for example, where you can get your local chlorophyll. No? Take the Gaussian pigments that we're going to export, test it with your chlorophyll, and get your own thing. How much more time do I have, Aina?
It's 1 minute till 10, but you can go.
Oh, no, it's okay. That's PCCs. I think maybe you guys are going to get some code for the GPIG.
I just sent it in the Slack channel.
Okay. So GPIG, there's a finally GPIG. Okay, one little side story. When you're developing an algorithm in MATLAB, for example, or anything else that you have to pay money for, and you're relying on some kind of magical math that happens in the background, like I do because I'm a biologist, when you take that algorithm and give it to us, that magical math, if it's like protected and copyrighted by MATLAB, it's very hard for us to make it. It takes some time for us to recode it. So think about that when you make the magic, like with the black box thingies that everybody likes to use these days. Think about what goes in that black box. It's very hard for us to replicate stuff. They're really not like open source like Python and stuff. Anyways, it's there now. You guys have a Python code. Play with it. It's going to be fun. Okay, primary productivity. Love this stuff. So primary productivity, as I said, is the photosynthesis that I measured. So this is the rate of that photosynthesis. It tells us how much carbon our phytoplankton converting into the yum-yum carbon that everybody else can use. And it's important for everything that we care about in the ocean, including dolphins. So this schematic is insane and just shows you the insane number of assumptions and formulas through which these input parameters are going in order to get to the end. This is a combination of several different algorithms, and I mean, there's a way to turn off things and turn on to see which algorithm takes which path. But the one that we currently have implemented is called CAFE. CAFE takes from our products spar, chlorophyll, APH, ADG, so absorption of the phytoplankton, absorption of the dissolved organic carbon and other junk, backscattering, carbon, backscattering slope, and then now it's taking sea surface temperature for a different source, and then it's taking mixed layer depth because it wants to know how deep are those phytoplankton distributed, and it's also taking some information like where it is and what day of the year it is. So it's a very complex thing. Some people will call it a model. That's why we're shoving it into probably level 4 data, okay? Because it doesn't rely only on satellite input and so on. You can see based on a number of parameters and number of lines, and this schematic that's making lots of assumptions and lots of things. So lots of things can go wrong, and that's why it took us a really long time to implement this. So this is pretty much a MODIS March 2022 image of a net primary productivity CAFE. We got it where we're happy with it. I'm happy with it. They have to be happy with it because I don't want to talk to them anymore. There will be differences between the Oregon State University product and our product, and it has to do with details that I can talk to you on the side, but pretty much how the pipeline goes. Once again, taking something that you run in your MATLAB or your Python or your local unit to take it to the big, industrial production takes time, and there are going to be differences. But we're going to be producing this. But just as you're going forward, and I don't have time to talk about, think about the assumptions that have been made in order to estimate how much a teeny tiny thing in the ocean is making carbon as you're using it and trying to write your nature papers. Anyways, I'm done. I have highlighted only some things. Find me, I'm here the whole week. Go on our website. We have documents, we have everything. Just in the end, PACE Ocean can tell you so much more and so much about the ocean. Everything what I spoke about is OCI-based, it's Ocean Color Instrument-based. I'm looking to force you to start using polarimetry data to tell me a little bit more. Think about it. Might not give you an exact thing, but it's an independent source of data that you can bring in to maybe just do some, I don't know why, maybe just bring some things better from the ocean or not. So yeah, and I'm almost in time. I am in my time. Just he went over time, so that's the thing. So yeah, thank you. I'm here. Ask me questions probably later, okay?